The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. All right, today we're going to look at section 11.5, part 1 and part 2. But before we do that, are there any questions from yesterday's assignment? All righty, I'll take that as a no. So yesterday we talked about the idea of log base 10, and that when we, let's say log base 10 of 5, that when we take log base 10 of 5, we don't have to put the 10 in the base. It's just assumed when it says log, okay? Because log base 10 is commonly used or is referred to as common log. There is another number that is commonly used, and that number is e. Now, it looks like a letter or a variable, but it represents a number, just like pi represents a number which is approximately 3.14159, etc., where pi is used in circles and spheres and circumference and area of round objects, etc. E is used where we have continuous growth or decay of something, or in the case of compound interest, where it's compounded continuously. E is approximately 2.71828. In fact, it goes on to be 1828. So it looks like it's going to repeat, but after that, it doesn't. So let's just say that pi is a little bit more than 3, and E is a bit less than 3. Okay, so E is approximately 2.7. All right, now, let's say we were going to graph y equals e to the x, okay? Again, e is a little bit less than 3, so if we were to graph 2 to the x and then graph 3 to the x, e to the x would lie somewhere between those two. But let's just go ahead and look at the graph of e to the x, at least part of it. And what I'm going to do again is I'm going to use -3 to +3, just to get a rough idea of what this looks like. Now, how do I get e to some value? On your calculator, recall that there's a button that says log, which is log base 10, and the second function key of that was 10 to the x. So we had log, and the second function was 10 to the x. Well, log base e is called natural log and is written ln. So ln stands for natural log, which means log base e. On your calculator, quite close to this log button, there should be an ln button, meaning log base e. And the second function key of that should be e to the x. And that's the button that we're going to be using to make our calculations. So back to this screen. So I want e to the -3 power. So again, because on my calculator, e is a second function key, I go second, then I push the ln button, which gives me e to the something power. I put in -3 and close it up. Oops. And then push equals. And I get 0.04978. I'm going to round that off and make it 0.05 because I'm only going to be approximating here anyway. All right. Is anybody confused about this? If you need me to pull up a calculator on screen, I will. But if not, I'll just continue. So let me know if you need that. All right. Next, I want e to the -2 power. So I'm going to go back up and use the same system, and I get 0.135, so that would be to the nearest hundredth, 0.14. Then e to the -1 is 0.367, so 0.37. E to the 0 power, of course, is 1, right? e to the 0 power is going to be 1. E to the 1 power is 2.7. Let's see here. E to the 1 power. 2.718, so 2.72 if we round. Oops, that's a 1. Okay, so this is 1, this is 2.72. E squared is 7.389, so 7.39, and E cubed is 20.085, so 20.09. And again, even though I rounded all my numbers to the nearest hundredth, I'm not going to be graphing it that accurately, but I just want you to get a rough idea. And again, get the idea that E is not a variable, it's a number. So let's see, at -3, we're at way down here, and then it climbs a little bit. It gets to about 1/3. Here we're at 1. Here we're at 2.72. Here we're up off the graph, and of course 20.09 is way off of this graph. Oops. Okay. Anyway, so it has that same shape as 2 to the x or 3 to the x. Again, any questions about that? All right. Now, I want to look at a new formula, and this is A equals PE to the RT, all right? This formula is, let's see what page is it on here. It's on page 951 in the textbook, but it's called the formula for exponential growth or decay. And let's talk about how a population grows or decays. Yakima County, okay? Is this what happens in the year 2021? Nobody is born and nobody dies up until December 31st, 2021. And all of a sudden on December 31st, a bunch of people die, a bunch of people are born, and the population changes. No, that's not how it works at all. Every day in the paper, there are death announcements and birth announcements. It's a continuous process, okay? It's changing all the time. So that idea of it being continuous. So a population tends to grow or decay continuously. Whenever we're looking at something like that that is continuous, that's when E is going to be involved, okay? Let's take the idea of compound interest that we looked at, I believe, yesterday. We have this formula, A equals P times 1 plus R over K to the KT power. That was when interest was compounded annually or semi-annually or quarterly or monthly or daily. But what if the interest was compounded continuously? Then we would use this formula, okay? Anyway, that's what we're going to be looking at here in more detail today, this new formula. So back to the formula, A equals PE to the RT. I don't know if it's still around, but there used to be a shampoo called PERT. So this is A equals PERT, except it's not PERT, it's P times E raised to the RT power. Okay, this problem says, find A using this formula, given the following values of P, R, and T. Round to the nearest hundredth. So that's going out 2 decimal places. It says P is 5,000. R is 8%, which we're going to convert into a decimal. And T is 20 years. Okay. So A equals 5,000 times E raised to the 0.08 times 20. Now, again, by using parentheses in my exponent, I don't have to pre-multiply it. I can, however, pre-multiply it if I want. And then it would look like this. Let's see here. 20 times 0.08 is 1.6. So I can either plug that into my calculator or that into my calculator. All right. So 5,000. Second, e to the x, and then I'm going to put in 1.6, and I get 24765.16212. It's said to round to the nearest hundredth, which is here. The 2 would round down. So our final answer would be 24,765.16. Any questions about that example? All right, let's take a look at another example. Let's see here. Again, we're going to use A equals P e to the RT power. And let's see, we've got P is 20,000. R is 10.5%, which would be 0.105. And T is 50 years. Again, be careful converting a percent to a decimal. You drop the percent sign and move the decimal point 2 places to the left. All right, so A equals 20,000 times e to the 0.105 times 50 power. I'm not going to pre-multiply it this time. I'm just going to leave it like that. So I've got 20,000 second e to the x, and then here I've got 0.105 times 50. Close that up. I get 381,132.5.369. So that's going to be 3,811,325.37, because again, we're rounding to the nearest hundredth. So to the thousandths place, the 9 would round up. Okay. Let's take a look at another example. In this case, P is 15,895. R is negative 2%, which is negative 0.02, and T is 16 years. R is the growth rate. It's negative. So this is a population that's actually going to shrink or decay. Our answer, A, should be smaller than P. Let's see what happens. A equals 15,895 e to the negative 0.02 times 16. Okay. So 15,895 second ln, which gives me e to the x, and then I've got negative 0.02 times 16, close it up with parentheses, 11542.138. The 8 rounds up, so 11,542.14. And again, it did get smaller, didn't it? So that's something that's decaying. Population is decaying. Okay. Next, it says evaluate each expression without using a calculator. All right. So again, recall that log base 10 is written log. Log base e is written ln. So ln, natural log, is the same as log base e. So the first expression is the natural log of e to the 5th power. That's the same thing as log base e of e to the 5th power. So this turns into that. Okay. Now, let's say that's equal to some unknown box. So now we're going to play an inning of baseball. We're going to change this logarithmic equation into an exponential equation. So e to the box equals e to the 5th power. So what's the box? It's 5. So the natural log of e to the 5th power is 5. Any questions on that example? Okay, how about this one? The natural log of e to the 4th power. Well, that's log base e of e to the fourth power. We'll say that's equal to some unknown box. Changing it to exponential form, e to the box equals e to the fourth power, so the box equals 4. How about this one? The natural log of 1 over e cubed. Well, that's log base e of 1 over e cubed. All right. So we'll say that's equal to some unknown. So e to the box equals 1 over e cubed. Well, I could write 1 over e cubed as e to the negative 3 power. So now the box equals negative 3. Okay, since the bases are equal, the exponents have to be equal as well. How about this one? The natural log of the fifth root of e. Well, that's log base e of the fifth root of e. That's equal to some unknown. So e to the box equals the fifth root of e. But isn't the fifth root of e to the 1/5 power, going back to chapter 9? So the box equals 1/5. Okay. Now it says to use a calculator to evaluate each expression. Let's find the natural log of 0.675. Now be careful. A little while ago when I was graphing y equals e to the x, I was using the second function key of ln. Now I'm just actually finding the natural log. So I'm going to push the button and it says this. Then I'm going to put in 0.675, whoops, 675, close it up, push equals, and I get negative 0.393042588. Again, it says to round, let's see here, 4 decimal places. So that would be here. The 4 would round down. So we're going to get negative 0.3930. Okay. Next, let's find the natural log of negative 10. Okay. So I push natural log, negative 10, close it up and push equals. And I get this answer. It says domain error. Recall yesterday we talked about that the base, if you have log base b of x equals y, the base has to be greater than 0. The quantity you're taking the log of has to be greater than 0. The answer can be any real number, but you can't take the log of a negative number and you can't take the log of 0. So domain error, meaning the input is not acceptable. Okay. All right. Let's see here. Let's do another one of those. Natural log of 2.7. So natural log 2.7. So go in 2.7, close it up, push equals 0.99325, etc. Here's the thousand or the fourth decimal place. This is going to round up. So 0.9933 would be the final answer. Now it says solve each equation. Express all answers to 4 decimal places. So I have the natural log of x equals 1.4023. And I need to solve for x. How am I going to do that? Well, natural log of x is like log base e of x. So log base e of x equals 1.4023. This is a logarithmic equation. Changing it into an exponential equation, we get e to the 1.4023 power equals x. So let's punch in second e to the 1.4023 power. And Again, it said, let's see here, to 4 decimal places. I've got 4.06453. So the 4th place would be there. The 3 will round down. So X is 4.0645. We all right with that? Any questions there? Okay, let's do another one of those. How about this? The natural log of X equals negative 0.001. So again, this is log base E of X equals negative 0.001. Changing this logarithmic equation into an exponential equation, e to the negative 0.001 equals X. So on my calculator, e to the negative 0.001 power, and I get 0.9990005. So rounding to 4 places, the 0 would round down. Okay, and you get that. Now, why wouldn't this be a correct answer? Because it said to take it out 4 places. So we need to put that, even though it's a 0, right? Placeholder value. All right. Any questions so far? Okay, that's it for part 1. So what I'm going to do, I'm going to go ahead and stop the recording. Okay. And we'll come back